All right. So last time we started talking about stochastic dynamics, stochastic processes, right? I tried to sort of impress you with the beauty of, stochastic sort of probability merged with dynamics and nonlinear dynamics. This was just one of the examples we worked through, but in general, we wanted to start thinking about systems where, because noise or some other uncertainty was entering the system, we now have to think about x of n as a random variable. And we wanted to stop thinking about the dynamics of any one rollout, right, and start thinking about the dynamics of the probability distribution, right? So we'd write the dynamics of some probability density in continuous space, right? So if I say that's the density of x at time n, then that we want to think about how that function evolves, right? And that function is sort of you can think of that as a view of the histogram of the function. It's just watching some particles fly around the system. But in general, it's a continuous function. Okay? And the beautiful thing, one of the many beautiful things, is that there's some cases where the trajectories of x were very complicated, but the probability distributions actually have very simple, elegant dynamics, right? And we talked about having a fixed point of this equation, which you could say would be sort of maybe p infinity of x would be sort of a fixed point of that dynamics, and those are called stationary distributions. Right? But otherwise, it's the same stuff. We're still thinking about dynamical systems. Functions now evolve over time, and a fixed point of the function has a stationary distribution. You can ask if it's stable. You can ask all kinds of these questions, right? And we talked a little bit about modeling, right? So the picture, I guess I didn't draw the diagram version of it last time, but the way I want to think about these systems is that I have, just like any system, I have an input. I often call it U, right? The outputs, we typically in this class think about the output as outputting state, but more generally I would call that some output function y and think about the state as the internal system. Oftentimes, so far, since we haven't done output feedback yet, we're still thinking of the output being the state. Okay? And the new thing here is that I want to capture the effect of randomness, not by changing my beautiful, hard-earned dynamics of my system, but allowing these systems to now have an additional random input. Okay. And in Drake, literally you can have a random source that outputs, there's a dent in the board. A random source that outputs the output of a stochastic process, a simple one, like a IID Gaussian noise or IID uniform or other things, okay? But actually, yet another reason to kind of keep that separate. Not only does it make analysis of this stuff easier, but the simulator, for instance, if you want to have all the more advanced simulation features that know how to take variable time steps to get accuracy, to do zero crossings, all these things that you've seen across the semester, if you start throwing random numbers in the middle of that, they're not going to be very happy with you. So we have a particular instance of this random source that declares itself correctly to the simulator, and it knows how to deal with that, for instance, right? So there's lots of good reasons to sort of keep that separate. And then my normal system is just the same kind of system that we've been writing the whole time. It's still governed by differential equations. It's just that they have that extra random input. Right? And we can define distributions over the initial x. And we can define the distributions over w, which is kind of what defines that random source. All right, so the goal for today is to start, so that was kind of the modeling and just sort of the intuition about the dynamics last time. And now we want to start thinking about the analysis and control design of these systems, okay? And it's actually an interesting thing. So it's a rich subject. I hope anybody who loves controls would take a class from Sasha Magretsky or one of the other great people we have on campus that could really dig into the mathematics of robust control. I will do a version of that, but there's kind of a joke, which is that even John Doyle, who's one of the sort of the luminaries in the field of robust control, he says that robust control is encrypted. Sort of historically, robust control has been extremely heavy on the math, even when some of the ideas are very simple, right? So like a standard paper on robust control would open up with like assume a Banach space, which is true and good, and that's, but like, you have to get to page, it's kind of hard to back out sort of the simple ideas really that are underlying that advanced math. So my goal in these couple lectures is actually to try to bring the essence of that, but using the type of tools we've already used, Riccati equations and time domain instead of frequency domain. That's the goal. You can tell me at the end if I accomplish that. Okay, so there's all kinds of interesting questions. I mean, maybe we could take as a hypothetical, let's say I've got my UAVs. Okay, and it's going to fly through, I don't know, what's it called in Star Wars, the canyon? What is it? The canyon he has to fly through? I forgot. Okay, let's say there's like a choice. You have to go through this canyon or this canyon, right? And maybe, let's say, this one's like pretty narrow passage, right? Pretty narrow passage. But let's say let's say there's no wind here. Okay, and maybe over here you've got a nice wide geometric sort of course, but it's windy over here, right? Which path do you pick, right? It depends, right? It depends on how your control authority, it depends on the magnitude of the winds, it depends how it affects your dynamics. But we'd like to sort of have recipes, tools that will help us make those kind of decisions, right? So there's a lot of different formulations that one could start with, and that people sometimes distinguish between robust control and stochastic control. I think that distinction is pretty small, okay? But stochastic control often is doing expected value, average kind of things, and robust control is often doing worst case kind of things. But I think the distinction is pretty. There's lots of examples where they're much closer. But in general, I think we need to decide how we would even write our objective. We're using optimization, we're using optimal control. How do you even specify the objective? Okay, so, I mean, we have now probability distributions, like the quantity that's sort of flying around is our probability distribution over x, and it's a function, right? So how do you write an optimal control problem about the probabilities over x? I mean, you could imagine having a desired distribution and writing a cost function that was sort of like how close is the actual rollout distribution, minimize the distance between my desired distribution and the actual distribution. That's actually not as common as it, I mean, it's probably more common these days because we have better, I think machine learning has brought a lot of tools in that sort of space. But it's not as common to write that. Typically we find sort of simpler summary measures, like let's say I'd do the average cost. right? So let's say I have, the sum over L, X, N, UN. That's the way we wrote it before, right? But now xn is a random variable, so I think a reasonable thing would say I'm going to take the expected value of this, over whatever my initial conditions and my probability distribution over W, right? That sort of defines this. And I'm going to say, let's just take the average cost. And we'll see that's a very common choice because it plays so well with Riccati equations and Bellman equations, okay? But that's not the only choice. You could say, what if I want the worst case? Cost, right? So let's say that W of n was drawn from, I don't know, some big but maybe bounded set, okay? So if I have a uniform random variable or just know that it's going to be drawn from some set. Gaussians are bad for worst case because they have some probability of picking extremely large numbers. They're unbounded support. So typically you'd say W's drawn from some compact set, okay? And then you could say something like, I want to minimize over U the worst case, the max over, let's say, my initial conditions and my noise of the sum of L of X U. Right? That would be kind of a guaranteed cost control if you could find that. You say, I don't know what my cost is going to be exactly, but the worst it could possibly be will be this. Right? And I should say, even even when people use this type of control, it is typically not. It is not because we think we can make a true promise about the actual worst case that could ever happen in the world, but it happens. I think somehow being robust to some modeled, but maybe simple but modeled disturbances in this kind of a sense can actually be a good way to be robust in practice. You might look at this and say, it's too much to assume that I know the total worst possible noise input. That's too much to assume, right? So how could I ever use that formulation? But I think the view from robust control would say, it's actually too much to assume you know a probability distribution over W, right? This is like less to know. You just say, I just know my random values are going to be between -1 and 1. I don't have to tell you the full probability distribution. Here, I have to tell you the probability distribution over W if I'm going to calculate it. Right? So the philosophy here is actually that this is less of a specification, an easier specification to write, and you can still do strong things with it. Okay, and we'll see a bunch of variants of this kind of stuff, right? So we'll see. Maybe just to keep the list going on the same board here. It turns out that if you do want to do Gaussians in worst case, you can do that, but not the way I've written so far. You could do something like I guess I'm at 4. You could do relative worst case. These are the gain bounds, L2 gain and stuff like this. So basically you say, I want something like the total power in the signal like this, okay, is if this is big, okay, then I want my total error, let's say, my loss xn un, I want it to somehow be proportional to this, okay? I want to somehow say that I accept that if I stick in more noise, then I'm going to get more cost, okay? If I increase the covariance of my Gaussian, then my cost is going to go up. But I want the relationship. I want it to be the case for small noise. I get small cost, and I want to sort of bound that relationship. And I'll show the derivations of that. And there's a bunch of other ideas that you'll see. So people talk about value at risk. Some of the things you've seen in economics, for instance, value at risk kind of metrics, or CVAR if you've ever seen conditional value at risk. These are kind of the robust metrics that, in general, you want some summary of your probability distribution that turns it into a scalar objective for control, okay? And I'd say the complement of that is sort of how do you write constraints? If we want to do constrained optimization, and there's really only a couple ways that people do this, okay? One of them would be sort of the chance constraints. Let's say I have an original constraint saying I want g of x to be less than or equal to 0, right? Maybe I have to write that instead, in my probabilistic sense, as I'd like the probability of g of x greater than 0 to be less than some scalar alpha, right? You could somehow say, I want to bound the probability of constraint violation. And maybe you'd bound that at an individual time, at x at time 10, or maybe you have to say it over the entire interval. Okay. Or you can do worst case constraints, absolute constraints. That would be the limit, sort of. That would be when alpha is going to 0. It's saying that I absolutely will not, no matter you find if an adversary is allowed to pick W, they cannot force me to violate this constraint. Okay, so that's kind of the rich palette that we're going to work with. And the story is basically the same kind of story that I've told you throughout this semester. There's a couple cases where we can solve this perfectly and understand it exactly. And then there's the full nonlinear general case where we have to carry our intuition from the simple problems, simple formulations, up to the full problems, right? And we can write nonlinear optimizations that will approach the nonlinear dynamics case, but our mileage will vary depending on the instance. So I think it makes sense to, once again, think a little bit carefully about some instances of the simple problem in an attempt to then go to the harder things. Right? So and it's really the same cases. It's always the same cases, right? There's basically two things that we really understand completely in control, and we can write it pretty much anything about. One of them is that sort of the tabular cases. I'll say we know everything. That's a little overstatement, but okay. We have powerful tools, right? One is the tabular setting. So finite state and action space. And the other is the linear optimal control setting. So I'll land what I think are a few key ideas from those, and then we'll push out, okay? Any questions on the basic sort of landscape here? Yeah. That's an obnoxious thing for me to say, but I mean that we know, roughly, if you give me one of these formulations, I can tell you how to solve it for those kind of problems, or that it's unsolvable, right? There's still new work happening in sort of finite sample results and other things. There's still active research going. But I would say most of these we know how to transcribe. Yes?
For specifying objective and using the worst case cost, isn't there a scenario where it's suboptimal, or the view that we get is suboptimal because the worst case cost or the worst case certainty is very unlikely?
Yes, that's a great. So yeah, so oftentimes people associate worst case control with sort of conservative control, right? You might not be able to. I mean, if you also had your objective, it might be that on average you're going to do poorly, okay? But you have a guarantee on the worst, right? And there is also recent work that's trying to sort of make a kind of an adaptive controller, which has some worst case guarantees, but then as you learn the distribution over W online, you can migrate from this control to the average cost control. There's things like that, okay? But traditionally, yes, robust control can be associated with conservative control. Yeah.
Yes, in this course, we've talked a lot about noise, like in a classical control course, sort of take a different approach to
Yep.
So I guess I'm trying to tie the two together.
Good. Yeah. Good. So yeah, in a class on linear controls, you'd see things like you'd be able to talk about stability margins and things like this, and you would maybe fit your transfer functions from data. I think all those things have analogs here. The stability margins that we talk about in linear controls sometimes don't go to the distance into nonlinear control, but I should be able to make connections to all. Hopefully, some of those things will connect here. The one thing is I don't do frequency domain here, even though I said most of the linear stuff has a beautiful frequency domain interpretation, and it's favored, I think. And that doesn't traditionally go into nonlinear dynamics as naturally as the time domain state space. So there's a bias here towards doing the time domain version, but almost always one could convert and see the same thing. Great question. Okay, let me tell you just a couple examples of like how tabular can shed some insights on what we've already seen, for instance, and what we could potentially solve for, right? So remember that the dynamics we've written down here, we've said that if we write it in the sort of probabilistic form, I'm going to say the probability distribution at xn plus 1 is a probability. The dynamics sort of is a conditional probability, saying if I'm in this step, if in x prime here at time n, what's my probability of transitioning to xn? This is sort of my dynamics, if you will, written in a probabilistic form. And we saw that, for instance, if you have a additive Gaussian noise, then that dynamics looks like, for instance, a Gaussian with its mean on the nonlinear dynamics, right? If I had xn plus 1 equals f of x n un plus wn, this was IID Gaussian, then you can write this whole distribution as something, e to the x minus mu squared. I mean, something like this, where the mu is f of x u. Right? This thing looks like the dynamics. The mean shifts, but it's a Gaussian added on top of that. So that's kind of the way I go from this F representation to this probability representation. There's a normalizing constant and stuff, right? Okay, so the tabular setting, of course, makes this equation even easier. the tabular setting, I get to go from functions back to discrete vectors. Right? So I could write this as, well, I'm going to use S just for discrete state here. And that can be written as a vector. Right, so I'll call it B today. B of n, where B of I is the probability of n, probability at time n that I'm in S of I. That's just kind of changing back to slightly more familiar notation. Right, so I can represent my state in these tabular systems as, this is the probability that I'm in state 1, the probability that I'm in state 2, just a list of probabilities. And then I can write my dynamics function similarly as a matrix now, right? So Tij, the matrix, whoops, I wrote I twice. Ij, that's going to correspond to probability of Sj conditioned on Si. Note that I had to flip the indices here, okay? Which is a little weird, but that's how we stay with, a lot of times people write this as a right matrix multiply, but I'm going to keep it as a left matrix multiply, because I want to be able to say now that B of n plus 1 is just T times B of n, okay? In this simple case of tabular dynamics, probably, no matter how interesting of a system we've written, the dynamics of that belief are just a linear matrix multiply. Right? T might be complicated. I mean, the numbers, it's still just a matrix, right? It's a numerical matrix. They might represent something very interesting, but we can evolve the dynamics in that way. And because of that, we can reason about the long-term dynamics, stability, convergence, very easily, right? We can ask what's a fixed point of B? Is it stable? We can optimize controllers that try to maximize that stability. Everything's clean and good here, okay? So let's just maybe point out real quick that we know that Tij, because it represents a probability, we know it's going to be between 0 and 1. That's not an arbitrary matrix T. It's a special matrix T. It's called a stochastic matrix. And we also know that along one of the columns, along one of the directions, the sum has to be equal to 1, right? So if I know Si, then the sum over Sj's has to equal 1. This is a stochastic matrix. It's a left stochastic matrix if you care, but okay, so if I want to think about the long-term dynamics of this thing, it's just a matrix, right? So I can say that B of n is just T of n times B0. So if I want to take n to infinity, okay, that's sort of easy. I just I can tell everything about the evolution of this by just looking at the eigenvalues and eigenvectors of t. Okay? It's just like a discrete time system. Stochastic matrices their eigenvalues are all going to be, all the eigenvalues are going to be also between 0 and 1. That's a nice feature, okay? And lambda max equals 1. There's always going to be at least one eigenvalue that is 1. Okay, that comes from this constraint. It's easy to show, but a stochastic matrix always has one eigenvalue of 1. What does an eigenvalue of 1 correspond to in a discrete time system? Right, an eigenvalue of 1 says if I take t and I multiply by that eigenvalue, then I just get that eigenvalue. The eigenvector. I multiply by that, I get 1 times the eigenvector, yes? So that's the eigenvectors associated with this, if you will, are a fixed point, aka stationary distribution. And then I won't go down the rabbit hole, but if you make just a couple assumptions about the matrix, a couple additional assumptions about the matrix T, about it being irreducible and aperiodic, and then you can basically say that there's exactly one fixed point, and that is globally stable. That's a very common system for your systems, as long as they have some basic assumptions met. Okay, so we can find fixed points of this thing very easily once we're in the tabular setting. So let me just sort of put that in context here. So remember we did this little example, right? And I simulated a whole bunch of particles. I actually, relatively a lot of compute hiding behind there, considering it's such a simple problem, right? And I'm simulating that forward. And my histogram, I don't have enough particles for it to really settle down, but if I had a lot of particles, it would eventually slowly converge to the sort of this fixed point that we know is sitting there. Okay. A different approach, which I almost finished for lecture, didn't quite finish my code, okay, but a different approach is I could just I could discretize my state, right? So if I just make a bunch of samples, let's say from -2 to +2, I just make 100 samples, and I fill out the transition matrix T that matches that dynamics. I could just solve for the fixed point. I don't have to simulate millions of particles forward. I can just take an eigenvalue problem. I'll find the single eigenvector associated with the eigenvalue of 1, and I could plot that distribution that looks just like this, right, in the end. Right? Just solve for it. That's beautiful, right? That's way more efficient than what I did here. Yes? Good, good, good. So he says, what about the other one? I have that ready. So yeah, what happens? I was going to ask you that. You took my question, right? So what would happen on this one? I did exactly that same numerical recipe. I binned it from -2 to 2, made 100 bins basically, computed the one-step transition probability for each of those bins. Right? That's an easy thing to compute. I compute the one-step dynamics, add the Gaussian noise. That's an easy thing to compute. What would happen here? Yes? I don't think so. But I understand why you say that. But my numerical recipe, the problem, he said, would it be singular? One of the artifacts of that numerical recipe is that it can't actually go to infinity. It goes to 2 and -2, right? So I almost finished it, but I didn't quite finish it. But I'm pretty sure, I'm going to put money on this, that it would have, the stationary distribution has mass at -2 and 2. yeah, with a little bit of tails because there's going to be artifacts of it going back and forth, right? Yeah, I think that's what it is. But here's the other thing, right? So this shape right here is another kind of Gaussian that's distributed here. It's going to have an eigenvalue of like 0.99 or something like that, okay? I know that you will find that this particular system has, because it has this sort of long-living transient, right? There's a distribution of points around this fixed point that hang out for a long time but slowly lose mass. So there's an eigenvector that has an eigenvalue that's close to 1 but not exactly 1. And so if you want to study these long-living transients, then you can actually study the second and third the eigenvectors corresponding to the second and third eigenvalues. Yes? Yeah, I mean, right, so there's definitely the truncation at the limits, and the discretization would also, I don't think it would be, it would break the analysis, but it'll be slightly less elegant. It'll be like taking histograms of my particles instead of having the pure function, right? But I think the transition probabilities, I don't think they naturally pool in some terrible way. I mean, it's very similar to what we did in value iteration. You could imagine cases where the decision boundary moved. Remember on that minimum time double integrator? You could imagine cases where there's bang-bang kind of solutions where that discretization would have a bigger effect. But for smooth things, I think it would be pretty benign. You could probably put bounds on it. So because you can compute this, you can compute all kinds of interesting things. Like if you wanted to compute the mean time to failure of your system, like what's the average time that a particle would take until it like goes to 2 or -2. That's just, again, that's like another function of the eigenvalues. Yeah? Yeah? Let me say it back to you in my words, but I think if you take observations of a discrete state system, then you can ask to learn the transition matrix. That'd be learning a Markov chain. And there's lots of good algorithms for and known results and bounds about learning Markov chains. Mm-hmm. Yeah. Yeah, for sure. If you have access to the function f that you kind of generate from, then that would be a simpler problem than what the learning Markov chain typically studies. That would just be you're getting observations that have to roll out into certain, it's like, what you said, I think, gave extra access, which is like you could put it in one state and take many samples. That's often not assumed, because that would be harder to do on a real system. But yeah, learning Markov chains is a big important topic. Okay, so you can compute all kinds of rich statistics about this. In fact, it's exactly what, when I showed you this examples of walking on rough terrain, right? I showed you a simulation that ran for a long time and then stopped, right? And we wanted to understand what's the mean first passage time. Like, what is the mean time to failure? How long will it walk on average, given a distribution of terrain, different walking, and then eventually with control? And we didn't have to simulate lots of things as time, for millions of seconds or whatever, with lots of different random variables. That would be a very, very inefficient way to estimate the mean time to failure. What we did is we took the return map and we discretized it finely, computed the one-step transition dynamics, and then just worked with eigenvectors and eigenvalues, and very accurately predicted the time to failure of those simulations. Right? So in the tabular setting, we sort of, I would say, policy evaluation, if you will. Is very well understood. Why do I say policy evaluation? Right? So what I talked about here is, given a closed loop system, there was no action there. But that is equivalent if I had a system that had a control input, but I had a fixed policy, and I do the feedback loop of the policy plus the plant, then I'm back to a system that has no control inputs, just like we did for Lyapunov, just like we did for everything, right? And so if I want to evaluate any one policy, it's analogous to looking at a passive dynamics, a closed loop dynamics, and we can crush that. We can compute a lot of interesting statistics with just linear algebra. Okay, what about control design, right? So for control design, again, we have to pick the way we specify our objectives, but this one I feel we've sort of already covered, but let me connect back, right? So for control design, the average cost is such a natural choice. It's not the only one. In fact, you can write pretty much any of those and understand how to work with them in tabular cases. But the average cost can be solved directly with value iteration. Right, just to spell that out, okay. So if I'm in my tabular setting, and I'm saying that the cost to go is somehow the min over actions, long-term actions, of my expected value of my sum right, over probabilities over S0, probability over W, if that's how I defined it, okay? Then the expected value plays exceptionally well with the additive cost formulations, right? So we chose in all of our dynamic programming stuff to say, I'm going to go ahead and restrict myself to costs that add up over time, right? And the expected value in the addition, the expected value of a sum of things is the sum of the expected value of things. And therefore, we can actually write the recursive form of this equation. We can take that expected value inside and say that this is write this as a one-step optimization plus the expected value of, let's say, the probability over the expected value over the next step, which then just becomes like this, yeah. And that's actually exactly what we were already doing in our value iteration algorithm. When I was discretizing and saying that to deal with the fact that the discretization didn't land exactly on another grid point, I was actually making a stochastic approximation of that, and value iteration just eats this up. Okay. So back in the day, we showed also that you could take a compass gate, and you could make it, if you optimized a deterministic function of walking stability, then it did a pretty poor job on rough terrain, okay? But if you optimized the stochastic version, then it walked very nicely over rough terrain. And that's the same thing when we showed the RL videos of the RL doing all kinds of things in crazy environments, right? That was because it was maximizing the expected return over a bunch of stochastic environment rollouts. If you wanted to compute the mean time to failure, you just choose a cost function that's basically 1 if you failed and 0 if you don't. And then the average cost is the mean time to failure. Right, so all these things are really nice. Okay, tabular is good and actually useful, right? I mean, not for big systems. It's kind of in the domain of things that we could discretize. Right? This is kind of almost resetting us back to when we were doing dynamic programming first. There's a class of problems that solve beautifully, right? And in that similar class of problems, we know how to solve the stochastic and robust versions. Okay, but let's walk through the semester, I guess. LQR, how can we do LQR on these things, right? For maybe bigger but almost linear systems, or linearized systems. what does LQR look like for these? So let me formulate it carefully, right? So I'm going to take the standard discrete time formulation, but I'm going to add IID Gaussian noise. And I'm going to say I want my cost, my average cost, to be the long-term, the expected value of the long-term x transpose qx plus u transpose ru, right? Let's see if we can do the infinite horizon version of it. What do you think is going to happen? Some of you might know the answer. Don't tell. Some of you might think you know the answer and might not know the whole picture, possibly. What do you think is going to happen? I tried to tell a picture, I give you sort of a picture last time of a linear system looking as a particle on a bowl, right? And we talked about two forces, right? We talked about the force of stability pushing you down and the force of randomness pushing you out, right? And having linear Gaussian systems arriving at a stationary distribution that looked something like that, for instance. So I think that's a pretty reasonable thing to expect to get out, is some sort of closed loop system that has a stationary distribution that, you know, stabilized, okay? But it's not going to get to zero. Okay, if we take something that's not going to get to zero and we sum it to infinity, that seems bad, right? Yeah. So the simple answer here is that J is going to be infinity. You know, fortunately, that's not the whole answer. It goes, there's a specific way it goes to infinity, and we can shape it, okay? But, for instance, if you do, let's say, reinforcement learning, undiscounted on an LQR problem, you will get infinity, and it won't work, right? You would need a discount factor to even make this work, okay? All right. In this particular setting, it turns out that it goes to infinity in a particularly beautiful way. Okay, so if you remember the original LQR, we said that the cost to go was a quadratic form, right? We know that's not the whole story here, okay? But it turns out that it's going to go to infinity. It's going to have a quadratic term that is actually nice and stable and good. And then it's going to have a constant term that goes to infinity. Okay? And we're going to see that the limit of Cn as n goes to infinity is infinity. But the optimal controller, which depends on this, not on this per se, is still well defined. And we can still choose a controller that minimizes this component and just kind of is immune to that, because the gradients of the, you know, the gradients that affect my decision don't depend on that, don't care about that scalar. Okay? Does that kind of make sense? So you're going to, there's still an optimal force that pushes you down. But because you're just going to be taxed for not being close to the, You're gonna basically, even if once you get to the stationary distribution, you're still going to just pay a tax on every time interval for all the probability mass that's not at 0. Right? So that's just going to accumulate, the tax goes up, but it doesn't mean I can't have an optimal decision. So this is one of the classic results. Okay, so you can derive it fairly easily. So, you know, I can write my exact discrete time equation. I'll get Riccati equations that roughly say that you get an equation of this form, okay? This is like the Bellman equation with the nonlinear dynamics inserted. And as you work it through, all of the components that multiply W, if you break up this term, so you get a term that is like W Sn plus 1 times Ax plus Bu. And since W is mean 0, and it's uncorrelated with this, that term disappears, right? And similarly, the other term disappears. And you basically get this is the recursion that tells us what Cn plus 1 is, and everything else is exactly the terms that we had in the discrete time LQR, right? You have that term. Okay, so huge result. Remember this, right? If you have a stochastic LQR problem with IID Gaussian noise, then the optimal controller of the stochastic system is actually exactly the same thing you'd get if you did the optimal control for the deterministic system. But your cost has this extra tax that runs to infinity. That's a big result, okay? Famous result. That does not mean, however, that it was, let's see, I still want you to believe it's worth learning stochastic control, okay? It is. It's worth, this tells you something beautiful, okay? This is telling you the right thing to do if you have IID Gaussian noise. But what happens if you don't have IID Gaussian noise? Okay, here's a great example, I think. Imagine you have a quadrotor blowing in the wind, or an airplane or something blowing in the wind, okay? Okay, I'll say I've got a UAV model here. I've got propellers coming in. I've got, let's say, state coming out. And I've got some model that tells me how the wind, when it's, W is wind this time, that's a coincidence. But the wind affects my quadrotor, right? There's some forces that come in from the wind here, and they affect my UAV. And I'll make this model in an example real quick, okay? The interesting thing, though, is that, you know, I have somewhere over here, I have a random source. This is putting out some sort of a W, let's say IID Gaussian. Okay, but IID Gaussian is a really rotten model for wind, okay? If the wind is blowing at 3 meters per second at time 10, then it is very likely to be blowing similar to 3.3 meters per second at time 10.01, right? It does not change arbitrarily at every sample interval, right? Okay, so how would we model that? The simplest model of that would be just to put a low-pass filter in here. I'll take a Gaussian IID noise, and I'll pass it through a low-pass filter. And there's a handful of famous wind models. There's the von Karman model. There's the Dryden model. Sort of famous, carefully characterized wind models out there. They're all low-pass filters with like super carefully contributed gains, I think. Okay. All right. So this is now super interesting, right? So if I do LQR on the UAV on this system and just ignore the wind, that's going to give me one controller, okay? But the LQR controller is not optimal for that system because this wind is not IID. If I want to drive a better controller that is optimal, then what I want to do actually, what this big result from LQR tells me is I should actually design a controller with LQR for this system. Yeah? Because this system, and well, I'll pull the U all the way out here too, right? If I design an LQR controller for that system, because this is IID Gaussian, then the controller for this system is actually an optimal controller. With one catch. What's the state of that? The LQR controller is a function of the state, right? So what is the state of this system is the combined state of the UAV plus the state of the wind. If your model is a simple low-pass filter, it's not that hard to write an estimator for the state of the wind. But that actually tells you that the right way to reject these disturbances is to estimate, write a simple estimator to estimate the state of the wind and the state of your quadrotor, and then just do standard LQR. That's pretty cool, right? This one I did finish coding up, okay? Here we go. I did it with my simple planar quadrotor here. Okay. So I added some wind, okay? So this is the LQR controller, but it's still being buffeted around by the wind, okay? And I can actually show you that it's really not that hard. I added a simple wind model here where I took the random Gaussian with two outputs, and this is the sampling time, okay? I just multiplied it by 2 because I thought it was too simple to have Gaussian covariance 1 for wind, so 2 was like somehow much better. More they put a system in here that I could configure the gain if I wanted to, right? It turned out 2 was interesting enough. And then I put a first order low pass filter in between there, and I just wired those up. Boop, boop, boop. Just basically exactly what I drew here. Okay, and I pushed that into here. And what you see is an output here that gets blown around in the wind. This is X, Y, and theta, okay? And it's getting buffeted around in the wind. Now here's the same setup now, but including the whitening filter. This is called a whitening filter when you take, this is, IID Gaussian is white noise. If you put it through a low pass filter, you get colored noise. Now it's got frequency content that is not uniform over the entire spectrum, so it becomes a colored noise signal. And if you're doing this sort of trick where you're using this to get back to a whitening thing, that's called whitening filter kind of process. Okay, so basically what I did now is I made this, first I made the system that is the quadrotor plus the wind, okay? And I just took that same gain and filter not this one, but this and this, and I made this diagram first. And then I called LQR on this diagram instead. And I ran it back around. Okay? And you run that. And it does a lot better. Same magnitude of noise and everything like this. It's not going to go deadbeat to the origin. It can't do that. It's getting knocked around. If I change Q and R, I could make it have a stronger response that fights it, but it's trying to balance these tensions between control gain, right, and the noise that's being pushed out, right? And it does a nice job of that, and the response is much better than the original LQR controller. Yeah?
And the LQR, you're trying to set, I guess, full state 0. If you're, I guess, you're only interested in setting Y 0.
Good.
So if you do LQR,
You could choose Q of, you have no control authority of this. So actually, what you choose for Q on this shouldn't matter, right? You have no ability to control that. You're right.
Oh, okay.
Yeah. If you chose Q with 0 there, you get the same controller as if you choose Q to be whatever. I'll be completely honest. I chose 10, 10, 10, 1, 1. Because this is a first order filter, yeah. And that's my, positions are always 10, and velocities are always 1. I could have set it to 0. That would have been more elegant. I might do that when I get home. Yeah, because it doesn't matter. Yeah. There's nothing that you can do, can do would affect that state. Yeah. I mean, if you have the ability to estimate the wind, yeah, I think that's better. Okay, so yeah, so if you have a source of disturbances that you think could be modeled as a linear modification of IID noise, then this would be better. Yeah. Mm-hmm. We actually did this on hardware, right? So this was actually the perching when we took it outside, right? And it actually worked most of the time, but there was definitely wind. And those poor little perching gliders just have no control authority, right? So like there's no propeller. When the wind wasn't there, it was awesome. It would do it. He was just throwing this thing, right? But if the wind came along, it's just long gone. Yeah. So that's what this is when I was trying to learn. This is a Mach power line. We were trying to do that, the B field based estimation of the location, and yeah, if the wind came, that plane had no hope, right? So we like, okay, we have to think this through. Thought about whitening filters. We bought this thing, which looks like it's from Honey, I Shrunk the Kids. It's a Doppler anemometer, which is awesome, right? You can measure the wind in 3 axes, right? And we fit the coefficients of our filter out in the Stata, deck area. It's not very Gaussian. It's not very, it's not very linear, but we had our best linear data, and the perching plane still had no chance. But we did build some, some simpler models that use that. Okay, actually, so one of the questions, back to your point, there's a famous result here, right? Do you guys know this? John Doyle submitted this paper. It's a very famous paper. The abstract is 3 words. And the story goes, actually, that apparently the first version of the paper he submitted is, do LQG regulators have a guaranteed margin or something? And his abstract was no. And the reviewer's like, we can't abstract. So, we can't accept an abstract that has 1 word. So he submitted this one, and they're just like, okay, fine. But okay, so LQG is the generalization of this, where we get the output feedback. But the basic result idea is the same. If you wanted to give me If you have a system that has Gaussian noise like this and you wanted to give a strict gain margin, you would not be able to do that. Not a bounded margin with this standard control. If you do worst case design, this is one of the papers that was foundational in sort of worst case robust control, then you can get those margins back. You guys had questions. I'm sorry, you had your hand up. Yeah.
It seems like if I'm making an individual robot, I should pretty much, and I'm going to do LQR, and I pretty much always attempt to at least try to model some of the noise or disturbance I would encounter and put it into my model. The world is not deterministic.
Yeah. I mean, people often don't. I think only when you have like an obvious present sort of thing that you would want to be robust to do people go through this extra step. It wouldn't be wrong to do it, right? I mean, even if your model of the noise was very small, it might have a very small effect or something like this. It's just extra cost in terms of estimation and feedback. Yeah. Yes. Good. Yeah. So the question is, what if we wanted to do somehow? I mean, I did a first order low pass filter as just a super simple case. So I think any class of linear filters could still be compatible here. If you get to like moving average kind of filters, then that's going to have more state. But any linear moving average filter can still have a state space representation, and it would have typically the state of the moving average as the dimension of the state space, for instance. So you'd have to do the state space realization, but then you could still do LQR and estimate those hidden states, and that should work. That's true. I think the LQR should still go through. It'll still do its best effort, right? And it does incur cost because of this, right? So it's not that the LQR pretends it's perfect. It knows that it's getting a bad cost, but it can handle systems like that. Mm-hmm. Do you have a question? So I think it could. I think the uneven so this part I actually wouldn't have a problem with for the uneven terrain. The question is, how does that terrain enter your dynamics, right? So here I used it as a force that was pushing around my center of mass. The linearization of that was still a nonlinear thing potentially, but the linearization of that was still sort of reasonable and good. I think the instantaneous to say that the terrain was drawn from a distribution, that is what we did for Runeless Wheel, but the internal map probably isn't, the linearization isn't a great way to control that map. I mean, on the full Poincare map, yes, it could work, but instantaneously we have to do more of the things we talked about with hybrid control. Yeah. Cool. All right, let me do one more sort of example, which is actually very simple. Just since we've been doing the stochastic control, let's just take it all the way to stochastic trajectory optimization, right? This average cost sort of view of the world. So let's say we have nonlinear dynamics, and we've done linearization to stabilize the upright, but we want to now, swing up and balance or perch on a wire or something, right? Then you can take the same ideas and move them up to stochastic trajectory optimization. There's a handful of ways to do it. One of them would be the iterative LQR that you talked about, that you've already done on your problem set. You could take linear plus Gaussian approximations of your dynamics across you would do a time varying linear Gaussian approximation along a trajectory. And you could do that. In the time varying case, I think the covariance the Gaussian approximation can change the optimal action. So it's not the special case of time invariant infinite horizon LQR, you get exactly the same controller out. The Gaussian didn't matter for the control. When you get to somehow these slightly more fancy derivations, then you do, the magnitude of your noise does change your controller. But there's an even simpler idea that I think is worth mentioning here. So if I have my fully nonlinear dynamics, right, and I want to optimize I want to minimize over U, right, the expected value, or maybe I do a direct transcription or whatever, but the expected value a very reasonable and practical way to do this, actually, is to do kind of what I did to make a lot of my animations, even my very first animation today, right? So what did I do here? I took a bunch of particles. Each of those is moving along, right? And you could think of this as if I took the average of those particles at time n, and I computed the cost, if I took the cost at every one of those particles, and I took the average of the costs, then that would be a way to sort of make a finite sample approximation of this function, right? Because I can write this as I can take the expected value inside. So a reasonable way to approximate this would be approximately equal to, let's say, the sum 1 over the number of particles, if I do, of x particle little k n u n, okay? A very reasonable and practical thing that people do is they'll take some small, typically less than for pure simulation, but some modest number of particles, and they'll simulate all of them forward, okay? Notice that I don't have different particles for the u. I have to pick one command that I get to send to the system, but I'm going to simulate k futures of that system, given some k particles in my initial distribution, right? And I'll evolve this forward, subject to, xn plus 1 equals f of x n. So let's say k u n. Now here's the other trick. For simulation, I'm totally fine picking a different random value of w every time I need to evaluate the function. But to do it in stochastic trajectory optimization, it makes, that would give you bad gradients, right? If you took a step and then suddenly the noise was different on this next step, that's going to mess you up. So you can call that a noise schedule or something like this, okay? What is typically done is at the beginning of your optimization, you'll pick big K times the horizon random numbers, and you'll freeze them for the entire duration of the optimization, right? So I've got K different instantiations of my noise and I'll fix those during the gradient-based optimization. Right? So it's really like you've instantiated k different players, and then you're taking this finite sample approximation of that to do the expected value computation. That is an approximate version of the true averaging, okay? But here's what I really like. Remember the thing we talked about last time quickly about the way that, for instance, randomness smooths contact. Even though this is an inelegant approximation of the true integral, let's say, over a complicated distribution, this can already enjoy some of those benefits of having sort of smoothing effects on the dynamics, right? Just shooting handfuls of particles out gives you that sort of smoothing effect. Imagine if I was, I don't know, just another simple example. Imagine I was throwing a ball over the wall, right? And I was doing some sort of simple trajectory optimization, throwing a ball over the wall. If I consider only one trajectory at a time, then there's a very discontinuous landscape, right? If I take my initial velocity and I lower it a little bit, then suddenly I'm going to go like this, right? Extremely discontinuous. If, however, I'm shooting a bunch of particles, a volley of particles with slightly different initial conditions, right? Then everything gets, even if it's a finite approximation, it gets much smoother, right? That as I change my initial velocity, let's say from something high down to something that's closer to the wall, then some number of these particles will experience this collision and move back, right? But the larger you get, the smoother your landscape will be. But then you sort of gradually turn on more and more of your particles will hit the wall and go back, okay? So I think an important lesson is that some of these stochastic objectives are better cost landscapes for optimization. And even low sample approximations can often make optimization better, right? You're optimizing a slightly different thing. You might not get what you want, okay? But it's often a smoother landscape. Yes? Yes, you get a lot of costs, a lot of constraints. Yeah. I would not, it could be an issue. Yes, so the efficiency of this optimization is going to grow with your k, right? It's basically like you're solving k trajectory optimizations at the same time, subject to the constraint that they all take the same actions, right? So it's going to be k times as expensive, almost, used, shared. Yes?
To clarify that, the optimization solve
You would sample your x naught and sample your w's. That's right. And then the cost function is the sum over those different costs. You know, the weighted sum over those different costs. Yes. You can do it in. You can do the direct transcription. You can do the shooting. Those are independent decisions. For either of those, if you sum the costs across all the particles, then you get this stochastic optimization. Good. Okay, we'll do more about robust stuff next time.